Example of solving a right triangle. This case is a little bit different. It only gives us two of the sides. It gives us the hypotenuse, side C, is 20 meters in length, and it gives us side B up here as 8 meters in length. So what it doesn't give us is an angle. So we're going to have to go looking for one. So the first one I'm going to go looking for is this angle up here, A. So we're going to concentrate on this angle and label the sides accordingly. So therefore, this side, the easiest one, is the longest one. It's opposite the right angle. That's going to be the hypotenuse. No matter what happens, that's the hypotenuse. And if we're looking at angle A, this side would be adjacent because it forms the angle A. So that's adjacent. Don't get it confused with this A over here, which is the vertex. Alright, so if I'm going to be looking for this angle, we're going to be dealing with adjacent and hypotenuse, which would be cosine. So the best I can say is cosine of this vertex A is equal to adjacent, which is 8, over hypotenuse, which is 20. Now the problem here is I need to solve for A, so I need to remove cosine. So what we're going to do is kind of get a little bit ahead in the book. As long as we're working in a triangle, this trick will guarantee work. Later on, it gets a little trickier, and we'll deal with that when we get there. So for now, we're just going to let the calculator do most of the work, and I want to undo what cosine has done to the A. And the way to do that is to use its inverse. It does have an inverse, yet we haven't defined it yet. So I'm going to cosine inverse both sides of this equation. So cosine inverse, of the left-hand side, and then we're going to do cosine inverse of the right-hand side. And I'm going to leave it as 8/20ths. You can reduce it if you want, but the calculator is going to do the work. So over here we're going to have cosine of A, angle A that is, and over here we're going to have 8/20ths. So just like all inverse functions, when they hit each other in a right triangle, this doesn't work for all angles, but in a right triangle, the cosine inverses will undo one another. So from that, we're perfectly fine saying that A is approximately the cosine inverse of 8/20ths. So second cosine in the calculator, 8 divided by 20, and we're going to get 66.4 degrees. So this angle up here is approximately 66.4 degrees. Now I could use subtraction to come up with this second angle down here, this angle B, and we can subtract 66.4 from 90, and we get this angle as 23.6 degrees. But I want to go the long way about it, just to figure out, do one more example of this inverse function thing. So I'm going to set it up so that we're looking for angle B given these two sides. Now, one thing is going to change. We've switched angles. The hypotenuse will stay the hypotenuse, but this side is not adjacent anymore. So I need to get rid of this adjacent side. The angle B, this side is considered opposite. So I'm going to relabel that as the opposite side of the triangle for this angle. And to find B, we're going to be using opposite over hypotenuse, which is a sine function. So I'm going to write it out as the sine of angle B is equal to opposite over hypotenuse, which is 8 over 20. And to undo this for a right triangle angle, we're going to use the sine inverse. So I'm going to sine inverse both sides. Don't read this as sine raised to the -1 power. So I'll sine inverse the left-hand side, I will sine inverse the right-hand side, and then just plug in what's on each of the sides. This side gets sine of B, this one gets the 8/20ths. Alright, and again, in a right triangle, a sine inverse and a sine will undo one another. So we'll be left with B is approximately sine inverse of 8/20ths. So if we do that, we'll get sine inverse of 8 divided by 20, which will give us 23.6 degrees, which is exactly the same as what I approximated earlier. And therefore we have almost solved the entire triangle. Now, you have a choice. You could use one of these approximate angles to come up with the third side, but I highly suggest you just use the Pythagorean theorem. It's going to be a little bit more accurate than using these approximate angles. So if you set up the Pythagorean theorem, that would be c squared equals a squared plus b squared. And in this case, the a, b, and c are perfectly labeled. C is 20, so you'll have 20 squared is equal to a squared is what we're looking for, plus b squared, which would be 8 squared. So a squared is going to equal 20 squared minus 8 squared. 20 squared minus 8 squared, 336. And then all we have to do is square root that, and we have our approximation. So a is approximately 18.3. And this is measured in meters. So this side is 18.3, and we have solved this right triangle.